Okay, so good morning. I have a couple of leftovers from yesterday's lecture because my friend Riccardo pointed out that a few things I said were not exactly correct, so now I correct myself. First one is the following. The three matrices tau 1, tau 2, and tau 3 deserve the name of generators of the SU2 algebra in the fundamental representation, in the sense that if you take a linear combination with real coefficients of these three matrices, then the exponential of I, alpha I, tau I is a member of SU2. And in order for this to be true, these three matrices must be Hermitian, self-adjoint matrices. For the same reason, tau plus and tau minus, which are defined like this, do not deserve the name of generators because they are not self-adjoint matrices. So this procedure is very familiar to all of you because is the procedure which is used in the Cartan method to determine the representations of the algebra of the rotation group. But anyway, these are not, strictly speaking, generators. The three generators are tau 1, tau 2, and tau 3. This is the first thing. The second one is that I said something about the unitarity of the Fermi theory, and I said that Fermi theory is not unitary in the sense that the S matrix which you get from computing amplitudes by the Fermi theory, at some point for sufficiently high values of the energy do not respect the unitarity bound. This is true, but of course it's true in a perturbative sense, in a sense in which the amplitudes are identified with the amplitudes computed at the lowest order in perturbation theory. If one were able to compute the exact matrix elements of the scattering matrix, then one would obtain a unitary, presumably a unitary matrix, but this is not possible in the context of the Fermi theory. And finally, I promised, you remember that we traded the two vector fields which are coupled to neutral currents in our construction for a new pair of vector fields, which I called A mu and Z mu, and the relationship between the two pairs is given by a matrix which I chose to be a rotation matrix. This is an orthogonal matrix. R transpose is equal to the identity matrix. And I promised you that I would give you a motivation for this choice, which I didn't. So I now keep my promise. And the reason is the following. You remember that the Young-Mills term for the full Lagrangian density has a term which is like this. Where B mu nu is equal to and of course, since the parameter theta w, which appears in R, is a constant parameter, is not x dependent, you have that B mu nu W mu nu 3 is equal to R F mu nu Z mu nu, where so if you plug this into this, what you get is and this is because of the choice of the matrix R as an orthogonal matrix. If you replace B mu nu and W mu nu 3 by this expression here, you get an R transpose here, or rather R transpose R, and this cancels because the matrix R is orthogonal, and you get again a diagonal term for the kinetic terms for A mu and Z mu. There is no mixing between the two, which would be nasty, because when you compute the propagator, what you would like to have is a quadratic part of the Lagrangian, which is diagonal in each field. So this is the reason why Glashow decided to rotate B mu and W mu nu 3 by an orthogonal transformation. So this completes yesterday's lecture, and we can start today's lecture. As I said, our next task is to include hadrons in the game. So far, we have only described the weak and electromagnetic interaction of leptons, the muon, the electron, and their neutrinos. And now we have to say something about hadrons. We already said that there is beta decay of nuclei. Beta decay can be interpreted as a decay of a neutron into a proton plus an electron plus an antineutrino. But in the context of the quark model, which I assume you all are familiar with, this can be, since the neutron has a composition in the quark model which is up, down, down, and the proton is up, up, down. The quark up, the up quark has charge 2/3 in units of the proton charge, and the down quark has charge minus 1/3 in units of the proton charge. So this is neutral, this has charge 1. So you can interpret this decay in terms of in the context of the quark model as the decay of the d quark into an up quark plus an electron plus an antineutrino. So what you need is a term in the hadron current, which is something like, I leave some space here for a reason that will be clear in a moment, U bar gamma mu 1/2 1 minus gamma 5 d. This is what you need in order to destroy a d quark, a down quark in the initial state, and to replace it by an up quark in the final state. It was clear very soon in the history of weak interactions that the up and down quark are not enough to describe the real world. The real world contains much more than this. In particular, it contains strange particles. There is a family of hadrons which you can produce by making pion-nucleon collisions at sufficiently high energies, and this new family of hadrons carry a new quantum number, which was called strangeness at the time, and it is still called strangeness. Strange hadrons are, for example, the lambda baryon, the K mesons, and so on. And this family of hadrons are produced in strong interaction processes, but they decay only by weak interaction. They have a strong production rate, but a long lifetime because they decay. Yes? The reason for left projector is the same as the reason for left projector in... okay, since these are coupled to the weak lepton current and this has a left projector because of the measurement of the Goldhaber experiment that measures the helicity of the neutrino, which means that this is coupled to an hadron current which can contain both gamma mu and gamma 5 in principle with arbitrary weights. Then of course you can factorize the coefficient of gamma mu and give a name to the coefficient of gamma mu, gamma 5, and it turns out experimentally that this coefficient here is very close to 1, and in fact it is exactly 1. This deviation from 1 is an effect of strong interactions only. So you can have a left-handed production even in the hadron sector. So you have strange hadrons, and strange hadrons decay through weak interactions, and what you need is to introduce a new quark, which is called S. The new quark carries strangeness quantum number equal to -1. Don't ask me the reason for this minus sign. I never knew. And the electric charge is the same as the electric charge of the down quark. So it was soon recognized that what you need here is another term which has the same structure, but with an S quark in the place of the down quark of the previous current. And it was Nicola Cabibbo who recognized that the relative weight of these two terms in the hadron current are in the same ratio as the cosine and the sine of an angle, which is called the Cabibbo angle since then. And the Cabibbo angle is a small angle, 13, 12 degrees, something like that. The weight of the charge hadron current which governs beta decay is much larger than the weight of the charge current term governing strange hadron decays. This is phenomenological. This comes from the measurements of the lifetimes of the lambda baryon, of the K mesons, and so on. So one would be tempted to proceed as in the case of leptons. I can write this like U bar L gamma mu times a linear combination of the down quark and of the S quark Dirac fields, like this, cosine theta w times d left plus sine theta Cabibbo S left. And again, I can cast this in the form of a Neuter current by introducing a triplet of left-handed quarks where this matrix here, which I don't dare calling a generator, is 0 cosine theta Cabibbo sine theta Cabibbo 0, 0, 0, 0, 0, 0. Well, this looks nice. I can observe that there is also the Hermitian conjugate current, J mu hadronic, which is just the same with T minus, T plus replaced by T minus, and T minus is simply the transpose matrix of T plus. And if I do that, I should proceed as we did yesterday with tau plus and tau minus and compute the commutator of T plus and T minus and check whether it is again a linear combination of T plus or T minus or not. And in fact, we find that it is not. The matrix T3 defined as the commutator of T plus and T minus, you can compute is something like, copy it, don't remember the signs. Well, I think it is, well, I do it. I can guess it. It's the generator which I get by taking the commutator between T plus and T minus is not diagonal. This is a difference from the case of leptons. It is not, it is, it has got off-diagonal terms in the ds sector, which means that the current J mu hadronic associated to this third generator is something like, probably there is one here, I don't remember. There is probably one here, I'm not sure about that. Anyway, if there is a one there, you have u left bar u left minus cos square theta Cabibbo d bar left gamma mu d left minus sine square theta Cabibbo s bar left gamma mu s left, and these are the three diagonal terms, plus you have an off-diagonal term which is minus sine theta Cabibbo cosine theta Cabibbo times d bar left gamma mu s left plus the Hermitian conjugate s bar left gamma mu d left. So this is again a neutral current because D and S carry the same charge quantum numbers. They are both charged minus 1/3 quarks. But this is a flavor-changing neutral current. While these three pieces here are flavor-conserving, they destroy a quark with a given flavor and they replace it by a quark of the same flavor. The same is not true for this last term, which destroys, for example, a D quark and replaces it by an S quark. This is a flavor-changing neutral current. And flavor-changing neutral currents are not welcome, for a reason I will tell you in a moment. Let me just complete the argument. You find that T plus minus T3 commutator is again proportional to T plus minus, so the algebra is closed. In that sense, we are done. We have no more currents in the game. Let me tell you why flavor-changing neutral currents are not to be included in the theory? Well, the point is very simple. They are phenomenologically excluded. It is very well known that flavor changing neutral current effects are very much suppressed with respect to flavor changing charge current. And a typical example is the decay of K mesons. Let me if you consider, for example, the meson K plus, which has a quark model composition U S bar. The K plus meson is formed out of an up quark and a strange anti-quark, which means that it has charge +1 and strangeness +1. And among the decay modes of the K plus, there is a beta decay. The K plus can decay into a neutral pion plus, into a charge. No, it was correct. Neutral pion, E plus an electron neutrino. This is an allowed decay mode. The branching ratio is around 5%, so it is sizable. And this decay is clearly mediated by I have to replace the the up just a second. Yeah, this is a piece I need. I have to replace the S-bar quark by an U quark. So what I need is a term like U bar gamma mu 1 minus gamma 5 S, or rather its emission conjugate. And this carries away sine theta Cabibbo. But if I have a term like this in the Hadron current, I can imagine that the same, the decay of the same particle can take place like this. And this decay process is given by the replacement of the S-bar quark by a D quark, because the pi plus is U D bar. And the weight for this is sine theta Cabibbo cosine theta Cabibbo. And the leptonic part of the Lagrangian density is essentially the same. There is the only difference is that here you have a charged lepton, here you have a neutral lepton, but this makes essentially no difference because the mass of the electron is very small compared to the mass of the K meson, which is around 500 GeV. So if you have this flavor changing neutral current term around, what you would predict is that the ratio between the width for the decay process pi plus, plus E minus, divided by the width for k plus into pi 0, E plus neutrino, should be of the order of the square of sine square theta cabibbo cos square theta cabibbo divided by sine square theta cabibbo. The square is because this is the amplitude and the width is proportional to the square of the amplitude. All the rest is essentially the same, phase space factors, matrix elements, there is essentially no difference. So this is what I expect, and since theta cabibbo is a small angle, this is close to 1. Something like this. This is what I expect from this construction. What I measure is 10 to minus 5. This flavor-changing neutral current process, you see that in the hadron sector there is no charge change, but the flavor changes. So this is flavor-changing neutral current process. It is measured. It has a very small branching ratio, and the ratio between the two is of order 10 to minus 5. So this is an example of the suppression of flavor-changing neutral current effects with respect to flavor-changing charge current effects like this one. So this must be suppressed somehow. What we did is not correct. And there is a very well-known solution, which I want to show you. So this doesn't work. Let me write this term here on the same line, plus sine theta cabibbo u bar gamma mu 1/2 1 minus gamma 5 the S quark. The solution was proposed by Glashow again, Jean Iliopoulos and Luciano Maiani. And what I'm going to tell you about is usually referred to as the GIM mechanism of suppression of flavor-changing neutral current. And the idea is the following. These three guys suggested that there is a fourth quark, which they call a charm quark. There is a new flavor to be included in the game. And this new flavor has the same electric charge as the up quark. It is similar to the up quark. And they assumed that the interaction of the C quark, of this newly introduced C quark, with D and S is like this: minus sine theta cabibbo C bar gamma mu 1/2 minus gamma 5 D plus cosine theta cabibbo C bar gamma mu 1/2 1 minus gamma 5 S. So while the up quark is mainly coupled to D and weakly coupled to S, the opposite is true for the charm quark. It is only slightly coupled to the down quark, and it is strongly coupled to S. There is no sign, we are talking about mid-70s, 1973, 74, there was no sign, there was no need to introduce a new family of hadrons phenomenologically, but they just used the usual trick. They just assumed that the charm quark is so heavy that present-day experiments in 1974 were not able to produce charm hadrons, so there is no problem. You just push towards high masses what you don't see. But still, the charm quark is there, they said, And it is coupled like this. And this current here can be, this current can be written in the following form. U bar gamma mu 1/2 minus 1 minus gamma 5 d prime plus c bar gamma mu 1/2 1 minus gamma 5 s prime, where d prime and s prime are not the original flavor quark fields, but are rotated with respect to them by a matrix which is again a rotation matrix. Okay? So if I do that, let me call this matrix V. This matrix V has the property of being an orthogonal matrix, and if it were a complex matrix, it would be Hermitian. It would be unitary, sorry. And if I do that, you immediately see that we are again in the same position as we were in the case of leptons, because this can be written like this. U bar left, d prime left, gamma mu tau plus u left, d prime left, plus c bar left, sorry, there is not enough room here. C bar left, S prime bar left, gamma mu tau plus, C bar left, S bar prime left. Sorry? Bar missing. Is that correct? No bar here. Okay. Why is this a solution to the neutral flavor changing neutral current problem? The reason is very easy. If I now compute J mu hadronic 3, this is diagonal in U d prime and S d prime, so this is given by U bar left d bar left prime gamma mu tau 3 U left d left prime plus C bar left S bar prime left gamma mu tau 3 C left S prime left, which means U bar left gamma mu U left plus C bar left gamma mu C left. These are the terms corresponding to the 1, 1 entries of tau 3 in both terms. They are diagonal in the up quarks. Then you have terms with a minus sign in front, because of the second entry of tau 3 has a minus sign. Yes.
But now, why those generators are very identify them as matrices between prime fields before it was non-prime fields?
What's wrong with that?
I mean, if we expand prime fields, we'll get another matrix between.
Yes.
Right?
let me finish, maybe this answers your questions. The second term here corresponds to down quark, so d prime left, gamma mu d prime left, plus s bar left prime, gamma mu s left prime. But he doesn't like primes, so I get rid of primes. And right here. This doesn't have primes, so it's fine. And this I can write like this, minus d bar left prime, s left prime, gamma mu, d left prime, s left prime. Okay? Just a scalar product. This times this plus this times this. But now I use this definition here. And I get, let me omit the first two terms, which are already okay, minus d bar left, s bar left, without primes, v Hermitian conjugate, gamma mu, v d left, s left. But I choose, actually Luciano Maiani chose for me V to be an orthogonal matrix, a unitary matrix, so V dagger V is equal to 1. So this is U bar left. Okay? Is that what you were asking? There is no trace of the mixing between the two down quarks because in the neutral current, because of the fact that we chose cleverly the structure of couplings of the charm quark, and we don't see it, so we can do whatever we want. So this is the GIM mechanism, which requires the introduction of as yet unobserved particle, the charm quark, but for the rest is okay. It suppresses flavor changing neutral current at the tree level. So this is what Glashow, Iliopoulos, and Maiani suggested, and in fact, the charm quark was observed very soon. What was first observed is the resonance C bar C, which is called the J psi particle in the J equal to 1 state, is a vector particle. It was produced in the plus and minus collisions at MIT and at SLAC, and immediately after that also in Frascati here in Italy. This particle has a mass. The mass of the J psi is around 3 GeV. 3 GeV is actually an enormous number for the scale of energies available at that time, and this is related to the fact that the charm quark has a mass of order 1.5, 1.3 GeV, which was indeed much larger than the masses of up and down quarks, and also much larger than the mass of the strange quark. Anyway, we will talk about flavor again later in much more detail, but I just wanted to show you this historical path which led to the idea that quarks must come in doublets, and mixing between different doublets is not only possible but also required by phenomenology. So we have nothing else to do, essentially. We have a structure which is very similar to the structure of leptons. There is a doublet of left-handed d quarks in the first generation. There is a doublet of left-handed quarks in the second generation, and the structure can be replicated as many times as we like, provided that the down component of this doublet are mixed by means of a unitary matrix, which I call V. And the right-handed components are again placed into singlets of SU2. And the hypercharged quantum number, if we repeat exactly the same argument which we worked out in the case of leptons, we would end up with a relation which is the same that we get for leptons, Q equal T3 plus the hypercharge divided by 2, or if you like, hypercharge to Q minus T3. The difference here is that down type quark now, up type quarks do not have zero hypercharge. The hypercharge of, for example, UR is twice 2/3 minus 0. The 0 here is because right-handed particles are singlets of SU2, and this is different from 0, which is a difference with respect to the case of leptons, where the hypercharge of right-handed neutrino was 0. And this will lead to differences in the case of hadrons, which we will discuss in great detail later. I think this is all I wanted to say about the massless structure of hadrons, and we can switch to the next subject, which is the way masses are introduced in the Standard Model. I can erase everything. Let me just introduce the problem, then probably we make a stop of 5 or 10 minutes, and then we come back to the lecture. The problem is the following. There is a problem with vector bosons. And this you already know. In the Young-Mills construction, vector bosons are transformed under the action of the gauge group like this: U, A, mu, U dagger, where U is a matrix belonging to the gauge group, plus I over G U d mu U dagger. And this second term is generally non-zero because U is assumed to be a local transformation in the case of gauge theories. And if you have a situation in which vector fields transform like this, it is clear that mass terms, m square, a mu, what we call a mass term in quantum field theory is a bilinear term in the Lagrangian which does not contain derivatives. So this is the only mass term you can build out of a vector field, which is dimension 4 and Lorentz invariant. So m square a mu is not invariant, clearly. It transforms in itself. plus something. This is easily seen in the abelian case where a mu, this transformation laws becomes a mu into a mu plus the divergence of a scalar function, the parameter of the transformation, which means that a mu goes into a mu plus twice a mu d mu lambda plus terms of order lambda square. So a mass term is forbidden by gauge invariance. There is no way out. But there is a problem also with fermions in the case of the standard model. Because the standard model, the theory we are constructing together, is what is usually called a chiral theory. A chiral theory is a theory based on an invariance property which treats in a different way left-handed component and right-handed component of a Dirac field. So a mass term for a fermion, which is usually written like this, a Dirac mass term, not talking about Majorana mass term for the moment. Dirac mass term is like this for a given fermion psi, which can be written like minus m times this combination. If you decompose psi into the sum psi left plus psi right, then you easily discover that the diagonal terms are 0 because of properties of gamma 5. So you are only left with the term which mix the right component and the left component of the Dirac field. And if you have a chiral theory is one which transforms, for example, the left-handed component into itself times a phase, and the right-handed component into itself times a different phase, which in the special case of the standard model is 0. These are singlets under the action of SU2, then this is not invariant. This goes into minus m e to I beta minus alpha psi left psi right plus the Hermitian conjugate. So in the case of chiral theory, also fermion masses are forbidden. But we know we need both. We need masses for the vector bosons because the weak interactions are short-ranged, and we obviously need masses for the electron, for the muon, for the up quark, for the top quark. We need a very heavy mass. So we have to find out a way out of this problem, and the way out is something you heard about a little bit yesterday, but I will talk about that in much more detail. So we stop for a while, maybe, and we start in 10 minutes with this problem. Okay. Wait for the last arrivals. What we need is spontaneous breaking of the gauge symmetry. Which is an unfortunate name, as you probably already know. The gauge symmetry is not actually broken. We don't want to break the gauge symmetry because gauge symmetry is what guarantees that the theory is unitary and renormalizable. So this is not what we want. And in fact, we will not break the symmetry. We will just realize it in a slightly different way. I will show you how the spontaneous breaking of the gauge symmetry mechanism works in a simple case. Then we will extend it to the standard model, but the extension is rather straightforward. And the simple case which I will talk about is what is usually called scalar QED. Scalar QED is quantum electrodynamics for one single charge complex scalar field. Why scalar field? We will see in a moment. So what is scalar QED is very simple. I have a charge scalar field phi of x, and the Lagrangian density is d mu phi Hermitian conjugate d mu phi minus m square phi dagger phi minus lambda phi dagger phi squared minus, let me use Fineman gauge. In the Fineman gauge, the free field Lagrangian for the electromagnetic field is minus 1/2 d mu a nu d mu a nu. The Fineman gauge means that the gauge fixing term is equal to minus 1/2 d mu a mu squared. I would take a few lectures to tell you something about gauge fixing. I assume you more or less know what it means. But with this gauge fixing Lagrangian density for scalar QED is like this. We have a scalar potential here, which means terms in the Lagrangian density which do not contain derivatives of the scalar field, and these terms contain up to the 4th power of the field, again by the criterion of renormalizability. And this Lagrangian density is invariant under the transformation phi of x goes to e to I e lambda of x phi of x, where lambda is a real function, phi dagger e to minus I e lambda phi of x, and a mu to a mu plus d mu lambda. These are the usual gauge transformation you are familiar with since classical physics, actually. Provided the covariant derivative here is defined like this: d mu phi equal ordinary derivatives minus I e a mu phi. This is what is called scalar QED. There are equations of motion for the fields phi. Actually, scalar QED is more complicated than usual QED because there is one more coupling constant, the coupling constant of the scalar field with itself. The equations of motion are something like d mu d square plus m square phi equal to something, which I call j phi. J phi is a function of phi and a, and d square a mu. This is the miracle of the Fineman gauge. There would be another term here which disappears with this gauge fixing. D square is equal to minus j mu a, and j mu a is the usual current for charge scalar field, i.e. phi dagger d mu phi minus phi d mu phi dagger. D mu covariant derivative, sorry. The gauge symmetry you are used to is said, in this case, to be realized in the way of Wigner-Weil. This is a Wigner-Weil realization of the gauge symmetry, and the important fact is that the zero field configuration is mapped into itself. The field configuration will correspond to phi equal to 0 everywhere and at any time is transformed into the same configuration phi equal to 0 by the gauge transformation. This is homogeneous in phi. So phi equal to 0 goes to phi equal to 0. There is a different way to realize the gauge transformation in this case, and the different way is called the Nambu-Goldston way, the Nambu-Goldston realization of the gauge symmetry, which doesn't share this property. And the Nambu-Goldston realization of the gauge symmetry is defined as follows. I define the transformation, the transformed scalar field phi like this: e to I e lambda of x times phi plus a constant, which I call v divided by a root of 2, minus v over root of 2. Of course, phi dagger goes to E. This is a real constant. And the transformation of the vector field is unchanged. I will show in a moment that it is possible to write down a Lagrangian which is invariant under this set of transformations. Let me just observe that, first of all, these kind of transformations do not leave phi equal to 0 equal to phi, do not map phi equal to 0 into phi equal to 0. If I said here 0, you get something different from 0 in general. And the second important observation is that V, the real constant V, is now a new fundamental constant in our Lagrangian density. So such a transformation is only possible, it is only possible to define a Nambu-Goldston transformation for a scalar field, because V has the same transformation properties as the field phi under Lorentz transformations, and we don't want constants that transform upon Lorentz transformations. So this is only possible with scalar fields. Okay, how do I build an invariant Lagrangian? And if I assume that the gauge transformations are like this, it is quite easy. It is especially easy if I rewrite the transformation law for phi of x in this way. If I write it like this, it is obvious that phi plus v over root of 2 modulo square is invariant upon this kind of transformation. This transforms by multiplication by a phase, and a phase is square modulus 1. So this is invariant. So the scalar potential, which I can build with the constraints that it is invariant upon this kind of transformation and it is renormalizable, turns out to be a quartic function of this quadratic function of this quantity, so I can write it like this. Constant b is irrelevant, of course. And if I further require that the potential has a minimum when phi equal to 0, then you can work out a little bit and discover that the potential has a unique form up to an additive constant, which is lambda phi of x plus v over root of 2 square minus v square over 2 to the second power. This scalar potential is uniquely determined by these two requirements, the requirement or the three requirements: gauge invariance with respect to the Nambu-Goldston transformations, no more than 4 powers of the field, and minimum at the origin. So this is the scalar potential. I need a covariant derivative, and the covariant derivative is easy to work out. I define d mu of phi plus v over root of 2 as d mu phi plus v over root of 2. This is irrelevant because the derivative acting on a constant gives 0, minus I e a mu phi plus v over root of 2. This is again covariant in the sense that d mu phi plus v over root of 2 transforms as the field. It is easy to check. So, scalar QED with the Nambu-Goldston realization of the gauge symmetry is here I can erase. Immediately written. Oh, gauge fixing. The gauge fixing term here is, it is convenient to choose a slightly different gauge fixing term, which is called the Fineman-Tuft gauge fixing. And the Fineman-Tuft gauge fixing is like this, is minus 1/2. Instead of d mu a mu square, I have d mu a mu plus something, and something is proportional to the imaginary part of phi. The gauge fixing is arbitrary, so I can choose whatever I like, and we will see in a moment why this gauge fixing term is more convenient in this case. So Lagrangian density is d mu phi plus v over root of 2 Hermitian conjugate d mu phi plus v over root of 2 minus the scalar potential, which is written down there explicitly, minus 1/4 f mu nu plus gauge fixing term. This is scalar QED with this definition of the transformation of phi under the gauge group. Why do I like it so much? Well, first of all, let me observe that the Lagrangian is still renormalizable. It still gives rise to a unitary S matrix because the gauge symmetry is still there. I have just defined it in a slightly different way, but it is still a gauge symmetry, so nothing has changed. We haven't destroyed the good properties of ordinary scalar QED. I need the scalar potential. And I need the covariant derivative. So let me write the scalar potential here. and the covariant derivative is written there. I write it here, so I have some. Okay. Let me first collect in a term which I call L0 all the quadratic terms in the fields. The quadratic part of the Lagrangian is important because it is the part which allows us to determine the shape of the propagators. It's the free propagating part. So what is L0? L0 has quadratic terms which come from the scalar potential, from the square of the covariant derivative, and also from the gauge fixing term, which is also quadratic in the fields. So I have to collect them all. This is just a matter of algebra. What do I get? I get a kinetic term for the complex scalar field. This comes from the ordinary derivative of the mu. Then I have a mixed, an interference term between the derivative of the scalar field and the field A mu from the square covariant derivative term, and this is plus I E V over root of 2 A mu d mu phi minus phi dagger. There is a phi minus phi dagger because there is a minus I phi in the covariant derivative and a plus I phi dagger in the covariant derivative Hermitian conjugate. So what you get is this term here. Then there is a quadratic term from the square of this term here, A mu times phi. And this is, I write it here, plus E square V square divided by 2 A mu, A mu. The square of this term, I, E, A mu, V over root of 2 is this term here. And this is a mass term for the vector boson. See, a constant times A mu, A mu. Then I have the derivatives of the vector field, 1/2 d mu A nu d mu A nu minus 1/2 d mu A nu d mu A mu. And there is another term proportional to the derivatives from the gauge fixing term, which is minus 1/2 dA square. Then what do we have? We have a quadratic term here, which is plus E square V square divided by 2 phi minus phi dagger square. And finally, I have an interference term here, which is plus I E V over root of 2 d mu A mu phi minus phi dagger. Very complicated, but I simplified it in a moment. So, what happens here? The first interesting thing is that the sum of these two terms, the second term in F mu nu, and the gauge fixing, the part of the gauge fixing term which depends only on the vector field, this is a total derivative. It's d mu of something. You can prove it very easily. So I can drop it altogether. Total derivative has no effect on the equations of motion, on the stationarity of the action, so I can just forget about it. And this is exactly the same as in the case of the Fineman gauge for standard QED, for ordinarily realized QED. Then look at these two terms. These two terms are particularly unpleasant because they are quadratic in the fields, but they mix the vector field with the divergence of the scalar field. But if I perform a partial integration, for example, in this term, and I assume that the fields vanish at infinity rapidly, then you have a minus sign here, and the derivative is acting on phi minus dagger, and these two terms cancel exactly. So I cancel this against this, and this explains why it is convenient to use this Tuft gauge fixing term. The Tuft gauge fixing eliminates the mixing between a mu and the divergence of the imaginary part of phi. Oh, they cancel because they are exactly the same, except that here the derivative acts on the mu a mu, on a mu, and here the derivative acts on the phi minus phi dagger. So I integrate by parts, and the derivative, the sign change, and they cancel against each other. So this simplifies considerably, and it is convenient to write phi in terms of a real part and an imaginary part, which I call respectively h of x and g of x. H stands for Higgs and g stands for Goldstone, and this should remind you of something you already saw. So if I do that, this L0 becomes simply 1/2 times d mu h plus d mu g, and this is this term. Then I have a quadratic term for, sorry, I forgot to write down the quadratic term in the real part. There is a quadratic term for the real part from the scalar potential, which is where is it? Minus lambda divided by 2 v square phi plus phi dagger square. So there are kinetic terms for the two scalar fields. Then I have mass terms, minus 2 lambda v square h of x squared, minus e square v square g of x squared. Then I have the derivative term for the vector field, d mu a nu, plus e square v square a mu. This is L0. I did nothing. I just defined the gauge transformation in a different way. So what are the propagators for this theory after quantization? There is I use solid lines for the field, for the Higgs field, the real part of the scalar field, and the corresponding propagator is minus 1 over k square minus 2 lambda v square plus I epsilon. So the mass, the squared mass of the Higgs boson is related to the parameter which enters the definition of the field transformation, which of course has the dimension of a mass because it has got the same dimension of the field phi. Then let me use a dashed line for the Goldstone field. The Goldstone field is a scalar, real scalar massive field with mass e square v square. So the corresponding propagator is minus 1 over k square minus e square v square plus I epsilon, which means that with this gauge fixing, the mass of the Goldstone boson is e square v square. And then I have a vector for which I use, as usual, a wavy line which has Lorentz indices at the vertices. And the propagator for the vector boson is G mu nu divided by k square minus E square plus I epsilon. So the Goldstone boson is massive as a consequence of the fact that this is not a global symmetry. This is not a global the breaking of a global symmetry, but it is the breaking of a local symmetry. And the Goldstone boson, which would be massless in the case of spontaneous breaking of a global symmetry, here has a mass. Actually, its mass depends on the gauge fixing terms, because the quadratic term appears here. And we will see that actually in the case of spontaneous breaking of the gauge symmetry, the Goldstone boson are unphysical degrees of freedom. We will get rid of them. So the situation is different with respect to the case of global symmetries, which you have seen yesterday. Okay, am I forgetting something? I don't think so. This is fine. So one of the problems I've listed at the end of the first part is now solved in principle. If I introduce scalars in the theory and I realize the gauge symmetry in this Nambu-Goldston way, it so happens that a vector field, a gauge vector field, acquires a mass term which is now compatible with gauge symmetry in the sense that it is not gauge invariant, but its gauge transformation is compensated by the transformation of other terms in the same Lagrangian. And the global thing is, in fact, invariant under the gauge transformation. So I have absorbed the variation of the mass terms into the variation of something else by means of this mechanism. We have half an hour, so we can go on and write down the interaction terms. Let me I want to study this model in some detail because it is a simple way of seeing how the physical content of the Higgs model is composed. Then we will extend it to the standard model in an easy way. So what is the interaction Lagrangian? The interaction Lagrangian is all the rest, all terms which are not quadratic in the fields. So it's just a matter of algebra to work them out. Let me write them down. There is a term which corresponds to the interaction of the vector field with the scalar field, and this term is like this: h d mu g minus g d mu h. Then there is a term like this, plus 3 I just list them, write them down. There is no particular difficulty in working them out. I wrote them in a column because I want to write here the corresponding Fineman rules, which will be useful for what I want to do next. And the Fineman rules are derived as usual. For example, This first term gives rise to an interaction term which I represent like this, a trilinear vertex with a Higgs line, a Goldstone line, and a vector line, insisting on it. There are momenta here because of these derivatives, and if I take PH and PG to be both incoming momenta, the Feynman rule is I, E, PG minus PH. You know how to get these Feynman rules from the Lagrangian density. You just take the virtual amplitude, you take the amplitude which corresponds to free particles as final state, you assign direction to the momenta, and that's it. We have no other term with momenta, so the rest is just a matter of computing the combinatorial factors. There are different ways of attaching external lines to the vertices. It's very easy. So let me just write them down. This term here is a solid line with two vector lines, and the corresponding Feynman rule is 2 E square V times G mu nu. G mu nu is because the two polarization vectors of A mu are saturated with each other. Then I have a trilinear vertex like this, which is minus 6 lambda V. 6 is 3 factorial. Then I have a vertex like this, 2 Goldstone and 1 Higgs. This is minus 2 lambda V. The factor of 2 comes from the two possibilities of attaching the two Goldstone lines. Then I have this one. This is like this. And this is 2 E square G mu nu. Then I have this one, which is also 2 E square G mu nu. And finally, I have minus 6 lambda for the 4 Higgs vertex, minus 6 lambda for the 4 Goldstone vertex, and minus 2 lambda for the 2 Higgs, 2 Goldstone vertex. So this is the complete set of Feynman rules for the scalar QED model, for the abelian Higgs model, which is how it is usually called, in the Tuft Feynman gauge. Well, there is an observation which we will reserve for the discussion session. We will need these Feynman rules at some point. Let me now tell you something about the physical content of this theory. Let me first concentrate on the free Lagrangian for the vector field, which has this form. You will agree with me that this is just the sum of 4 terms which are similar to the free Lagrangian of 4 real scalar fields. For example, let me write it explicitly. It is minus 1/2 times d mu A0 square minus
But those fields are mixed with Lorentz transformation.
sorry?
But those fields, scalar, they are mixed by Lorentz transformations, right?
They are mixed by Lorentz transformation, yes.
So like
I agree, but after you have mixed them by Lorentz transformation, you can say the same thing of the transform fields. Okay? So these are four Lagrangian for four distinct scalar fields. With the only difference that this component, the zero component of the vector field, has a minus sign in front of it. A minus sign in front of the Lagrangian means, you remember how you quantize a scalar field, right? Quantization of a scalar fields goes through the definition of creation and annihilation operators, and the creation and annihilation operator obey commutation rules, which are A of k, a dagger of q equal to delta k minus q, right? Now, if I change L into minus L, if you recall classical mechanics, this amounts to changing the sign of P of the conjugate momentum. And if you change the sign of the conjugate momentum, this is equivalent to switching A and A dagger. So if you have L transformed into minus L, what you get is a commutation relation, which is a K, A dagger, Q equal to minus delta K minus Q. Because changing the sign of the Lagrangian is equivalent to reversing the sign of the conjugate momentum. So, I can write the free field solution of the equations of motion for the vector field A mu like this. A mu of x, I can do it by mimicking the free field solution of a scalar field, of 4 scalar field, which I write like this, 1 over 2 pi to power 3 halves. This is conventional to get some given normalization of the commutation relations. Integral over the 3 momentum k divided by 2 the energy associated with 3 momentum k times destruction annihilation operator A, which carries an index mu and which is a function of k, times the propagating plane wave e to chi minus chi x, plus the Hermitian conjugate, plus a dagger mu of k e to plus I k x. The energy is plus root of m gamma square plus modulus k square. I am defining m gamma equal e v. And the commutation relations between A and A dagger are like this. A mu function of k, a mu dagger function of q. This is equal to delta k minus q with a minus sign when mu and nu are 0 and a plus sign when mu and nu are equal and spatial. So this is minus g mu nu. Yes.
I had a question. When you write the Fineman rules,
Mm-hmm.
in the Fineman Tuft gauge, do you sum over 3 polarizations for the boson, or?
No, I don't.
No, I'm asking. So you only sum over 2? Because
No, no, no. I don't sum at all. There is no sum in the derivation of the Feynman rules. If you have vector boson lines as external lines, you have to saturate them with polarization vector, and I haven't said anything about this polarization vector so far. But there is no sum here.
But I'm asking, does the vector boson have only the
I will show you in a moment. Just a second.
because you still have the Goldstone.
I still have the Goldstone. I'm going to show you what happens with the Goldstone. So these are the commutation rules for the annihilation and creation operator for the four components of the vector fields. Now, it is convenient to expand each of these 4 vectors in a basis which depends on k, which means that I will write a mu of k as a linear combination, a sum over lambda, and lambda goes from 0 to 3. There are 4 different directions in the space of a function of lambda and k times polarization vector, which I call epsilon mu, which is a function of lambda and of k. And I can choose the polarization vector like this. Since the vector is now massive, I can go to its rest frame and choose the 4 polarization vectors epsilon mu of lambda in the rest frame as the 4 unit vectors in the 4 directions. So I will choose epsilon mu of 0 in the rest frame. The second 0 is the 3 momentum as the vector 1, 0, 0, 0. Epsilon mu 1, 0. Which means that epsilon mu of lambda in the rest frame is just equal to delta mu lambda, right? There's only one component which is non-zero, which is like this. And after I have defined the 4 polarization vector in the rest frame, I can get epsilon mu in the frame where the vector boson moves with the momentum k by simply boosting them. Lambda is a Lorentz transformation, which is a function of the momentum, times epsilon nu of lambda. Yes, 0. Which is equal to lambda mu lambda of k. And if I do that, I can write these commutation relations in terms of this coefficient a mu. I just replace each a mu by its expansion over the basis of the polarization vector defined in this way. And then I just use the properties of the Lorentz matrices. I have to erase these beautiful Feynman rules. I will rewrite them when we need it. And what I get is a lambda k commutator with a dagger lambda prime q equal to minus, where is it? Minus g lambda prime delta k minus q. Sorry, it's a bit boring, but it is important and we need it. We need to show what I'm going to show you. So let us concentrate on the polarization modes with lambda equal to 0. If I take lambda equal to 0, then it is easy to show that epsilon mu 0 k is proportional to k mu. It is in fact k mu divided by the mass. This is easy to show because this is true in the rest frame. In the rest frame, the vector k mu has only the 0 component, which is equal to the mass, and 0 special components. So this is precisely k mu. And since this is a covariant relation, this holds true in any reference frame. So these modes with lambda equal to 0 correspond to a polarization which is longitudinal, which is parallel to the for momentum of the vector particle, which means that the corresponding field, if I write a mu as a sum over lambda from 0 to 3 of a mu lambda, this means that a mu corresponding to polarization 0 is proportional to the derivative of some scalar field, because the polarization vector is k mu, and if I plug k mu here, k mu times the plane wave is the same as taking the derivative with respect to x mu. So the longitudinal polarization mode corresponds to a scalar field. Is a degree of freedom which corresponds to spin 0 because it is entirely fixed by a scalar function. Furthermore, these lambda equal to 0 degrees of freedom are those which have the wrong sign in the commutation relation. A of 0 k commutator a dagger 0 q is equal to minus delta k minus q. And this means, this implies, as I will show you in a moment, I have 5 minutes to make this important proof, but I will do it. This means that the states, the physical states, the physical single particle states that you build out of these creation operators are states with negative norm. So they are unphysical states, they must be excluded from the physical spectrum. This is pretty easy to show because well, of course I have to form wave packets because single particle states are plane waves, they are not normalizable. So let me define a state with momentum k built out the polarization lambda equal to 0 like this. It is an integral over 3 momentum p of a dagger 0 p acting on the vacuum state of the theory with the state with no particle, times a wave packet, which I call f. This is a function of p, and this function of p has a strong peak around p equal k. This is a wave packet. This is something like a Gaussian, something like that. And now let me compute the norm of this single particle wave packet. This is easy to do. It is an integral over dp prime, integral over d3p, f complex conjugate peak around k function of p prime, f k p, and then I have a scalar product, vacuum state, a 0 p prime, a dagger 0 p, vacuum state. Now I use the commutation relation, which has the wrong sign. And if I use the commutation relation, I can commute these two creation and annihilation operator when A acts on the right on the vacuum state gives 0, and you are only left with the commutator, which has a minus sign. So this is minus 0, 0, the norm of the vacuum state, times integral. There is a delta function p minus p prime, which allows us to perform immediately, for example, the integral over p prime there. And this gives the integral over d3p times fk of p modulo squared. This is a finite integral because this is a wave packet, so it goes to 0 rapidly at p equal to infinity. And it is positive definite because it is the integral of a positive function. The norm of the vacuum state is assumed to be positive, and there is a minus sign here. So this is less than 0. So I have to get rid of states with polarization 0. The polarization state corresponding to lambda equal to 0 do not belong to the physical state of Hilbert space of states. And it is easy to get rid of them. The way you get rid of them is to require that the polarization vector are such that epsilon mu of k dot k mu is equal to 0. If you require that, you immediately exclude longitudinal polarization vector, because the longitudinal polarization vector is proportional to k mu, and k mu square is not 0. Yes? Not more or less, of the free equation of motion, yes.
So
Talking about asymptotic states, the states you measure in your detectors. The question is?
linear equation.
Yes.
So we can multiply the state on some imaginary factor to make it positive.
No, if you multiply by imaginary factor, and you take the norm, you get the complex conjugate, and you get the same sign. That doesn't change the sign. I have to stop. So I have to stop at 45. Oh, I'm sorry. Why didn't you tell me? I'm sorry. I'm very sorry about that. Okay, we go on tomorrow.